Welcome to Planet Geo, the podcast where we talk about our amazing planet, how it works, and why it matters to you. Vacation, Chris.
Yeah. Is it though? Like, I don't know. That doesn't really sit well. This is not really a vacation.
No, it's not a vacation.
We have so much going on in the background. I mean, it's not a vacation.
Yeah, that's right. It's a variety of exciting things in the works, as we usually do. I mean, at all times of the year, but especially in the holidays, we usually take a break from recording new content or producing new content and just re-release a couple things. But vacation, Chris, I'm curious. Winter vacation, Chris, what does that look like? Is that on the tractor with a big onesie, plaid onesie snowsuit, with a little dainty cocktail with an umbrella in it driving around?
No, none of that. But well, I mean, no umbrella, of course. There might be a cocktail with me, but not an umbrella. But okay. I just put the snowblower on yesterday, so I'm ready. Let's let it rip now. I can't wait to play. I just can't wait.
I love it. Okay, here's the deal. When you get sick of your tractor and decide you need a new one, I want a discount and I'll buy the old one from you, and I want a discount. How about that?
Yeah, you do need one. You know, to that point, I know it's just a little subcompact tractor, but I absolutely love it because everything has quick connects. So putting the snowblower on, for the first time doing this, it took me about 15 minutes to do, and it was so easy.
I mean, it hardly counts as a job, really. I mean, you shouldn't be bragging about how you put your snowblower on.
No, it was ridiculously easy to do, and I love that, though, because, I've had this before. I had another lawnmower that I had a snowblower, and I'd take it on and off, and it just took a long time. It was like a day to do this. It was just not something I looked forward to, so yeah.
Vacation, Chris. So, Chris, the theme of our re-releases here during our pause in releasing new content is, we decided to go with look back and each of us pick four of our favorite episodes that we have not re-released before. So some of them we had to kind of rule out because we've re-released them before in previous, holiday break times. I don't know. What was your thought? This was a partially easy, partially hard exercise, but we're about to start year 5, so we've got a lot of stuff.
Yeah, that was really cool. It was actually fun for me and to actually sit down with you and go through these and say, well, I think I want to do this. And you're like, well, we already released that once before. So it was just fun to go back and reflect on the episodes that we've done, and also like sitting back and looking at the sheer volume of material that we've pumped out. So it was fun. I got excited.
Yeah, it is. It's very exciting. And Chris, you just said that you ran into a former student at the local hardware shop there in Huntsville, and they said they just started listening to the podcast, and they started to go back to the beginning, which I don't know. That's interesting. I never do that with podcasts. I don't go back to the start. I just start from the most recent and decide if I like it from there when I'm like exploring a new podcast.
That's not my approach, Jesse. You
go back to the start?
No, I don't go back to the start. I'll jump in the middle. For some reason, what I'll do is I'll just scroll back and see a title that pops, and then I'll go from there.
Yeah, that's interesting. I hope that your student wasn't turned off, because when we go way back, we were learning, let's put it that way, in the first year. I would say the first year of content. Our audio wasn't great. We were learning. It's a little rougher than it is now.
But it is interesting, though, Jesse, that I feel like those early days, though, is when it was so easy to come up with content at that point.
Oh, that's true.
And so I think like we covered a lot of really cool things then. Maybe we need to go back and revisit those and do it again.
Some of those topics
again and see. I don't know. It might be an interesting exercise.
Chris, I think there's so much to cover. Like you said, we've got all sorts of projects in the background that we're working on. And I mean, there's just too much exciting stuff to cover. Too many interesting people to interview as well. Although it is fun to look back. So Chris, lead us out. The first one is yours. This episode is one of your favorites. So what is it? Why is it your favorite?
Yeah, this is all about carbon dating and the common misconceptions that surround it. And this is Chris Bullheis and the rabbit hole of social media. Why this is my favorite one, because I belong to these scientific Facebook pages or whatever, and then you go into the comment section on some of their posts, and people want to debate the age of the Earth and whether or not this was really 300 million years old and stuff like this. And I can't help myself. I go down this, and then it inevitably turns to carbon dating, and it's like, wow, no, we don't do. That's not a tool that we use, to do this kind of thing. And so I think this is a really important episode, and that's why I chose chose it.
That's why you chose it. Okay. Yeah. So this comes from June of 2022 when we initially released this episode. And I agree. This is an intro into the field of radiogenic isotopes and radioactive decay, and how we as geochronologists have this big toolkit, this big toolbox with all sorts of different tools that we can use. And some of them are great for specific applications and they suck for other ones. So I agree. This is a great one because it introduces the topic of geochronology, I think, at a really basic level. So,
well, Jesse, let's do it.
Let's get to it. There's a couple ways to support us. First of all, you can go to our CampGeo app. That's the first link in your show notes. Check that out. There we have podcasts with images, some of them available for purchase, and we're continuing to build new content out. You can also go to our website, planetgeocast.com. Send us an email, planetgeocast@gmail.com. Let's get to it. Yeah, man, this is Planet Geo.
Heck yeah, let's go.
We get to talk about all things geoscience.
Yeah, I'm really excited about today. Today, we're going to talk about carbon dating, and which is also called radiocarbon dating. And this is something that, like, I think everybody knows this by now. If they've listened to our podcast for a while, they know you're into dating rocks. Okay, and
very much so.
So this is your lane. It's your expertise. I have a lot to bring to it from maybe different perspectives and misconceptions that I come across a lot. I think this is one of the things that it's maligned a lot, radiocarbon dating, what it can do, what it can't do, what it's used for, how good is it? I think there's a lot of stuff that's just simply wrong about it.
Misconceptions about it, not that the method itself is wrong.
Yeah, you're right. People get a lot wrong about this topic.
Absolutely. So carbon dating, I always get this question in class. Why can't we date diamonds? Diamonds, most people know diamonds are made of carbon. They know carbon dating is a thing. I mean, people generally kind of know the words carbon dating maybe. And the question is, why can't we date diamonds? And we'll touch on that at the end, but basically diamonds are far too old. And you said, I like to date rocks, which is very true. I love dating rocks, measuring the ages of rocks. But radiocarbon or carbon dating is not very good for rocks, actually. It's actually really good for former organic matter, which makes it really, really, really useful, actually, in the fields of archaeology. It's very good for the last 50,000 years. And we're going to go through the details of why that is and why it's not good for dating rocks.
And it's only good, though, for dating organic matter that is younger than 50,000 years old. Some of the misconceptions that I encounter a lot, the misconception is we use radiocarbon dating for dinosaur fossils, things like that. And the bottom line is there's no carbon left, radioactive carbon anyway, to date in dinosaur fossils. So we can't do radiocarbon dating on things like this. And that is, to me, that's the most prevalent misconception that exists out there, is the dating of anything that used to be alive, regardless of how long ago that happens to be,
yeah.
Right?
No, that's totally right. I mean, I think I was just going through this. We've got a couple undergrads working in our lab doing undergrad thesis projects. And so I was in the lab working with graduate students and the undergrads, kind of teaching them the ropes of some of the techniques. And basically all these things, you got to learn the tools. You don't want to, try and drill in a screw with a hammer, right? Like, you got to use the right tool for your task at hand. And so radiocarbon or carbon dating is very different from other types of radiometric dating. And it just depends. Are you dealing with a nail or a screw? Like, which one do you use? Are you trying to date a young, burned down tree stump from some archaeological find? Then you might turn to carbon dating. If you're trying to date old rocks, you're going to turn to uranium lead or something like that. So all these techniques have different niches of where they're useful, where they're really useful. And there's overlap between them. But
so let's get into, Jesse, let's get into some of the basics about, okay, carbon 12, carbon 13, and carbon 14. What's going on? So these are basically three isotopes of carbon. And we need to get into a little bit of this, and we're going to go fast with this because I don't want to lose anybody on this. But basically, a carbon atom, anything that is called carbon, means that it has 6 protons in the nucleus. And the vast majority of all carbon is carbon 12. That means it has 6 protons and 6 neutrons for a mass of 12 atomic mass units, okay? There are 2 other common isotopes, carbon 13 and carbon 14. carbon-13, 6 protons, but it has 7 neutrons. So 6 plus 7 gives it a mass of 13 because protons and neutrons each weigh 1 atomic mass unit. And then there's carbon-14, the one that is at the center of our discussion today, because that's radioactive with this half-life that we'll talk about later on. And that has 6 protons and 8 neutrons. So they're all isotopes of carbon, which means they're the same atom, but they have different numbers of neutrons in the nucleus.
That is exactly right. And that extra neutron in carbon-14, where it has 8 neutrons and 6 protons, that extra neutrons, those make it unstable. So this nucleus is not stable, which means it'll break apart and it'll decay into something different. And what it decays into is nitrogen-14. So it decays through beta decay. So one of those neutrons is unhappy being a neutron, and it'll break down. It'll kick out an electron. A neutron is basically a proton plus an electron. So a proton, 1 mass unit and 1 positive charge, plus an electron, 1 negative charge, and basically no mass. So it's a neutral thing with 1 mass unit.
Let me back up a second. Okay, so beta decay, this is what happens with carbon-14 that decays into nitrogen-14. If you define beta decay to students, you're like, okay, beta decay is a high energy electron that is ejected or emitted from the nucleus of an atom. Some of them will question that. Like, wait a minute, but there are no electrons in the nucleus of an atom.
Yeah, aren't those whirring around outside of it? Isn't there some shell of electron shell?
And this, Jesse, I got to tell you, this leads to one of my most irritating things regarding chemistry. Like,
I can see the vein coming out of the forehead right now.
But here's what it is. And when I tell the students this, they actually get a little bit pissed off. Wait a second. This is what beta decay is. So how does an electron, which doesn't exist in the nucleus of an atom, how does it get emitted from it? Well, to me, like, it's such a weird thing, but I didn't learn this till I was maybe a junior in college and, taking a lot of chemistry classes, what a neutron really is. And you just said it and you glossed right over it, but it's lost on a lot of people. Let's look at, first of all, what's a proton? A proton is a positive charge, has a mass of 1, right? An electron is a negative charge with essentially no mass. It has such a small mass. It is 1,837th the mass of a proton. You're never going to deal with the mass of electron. So what do you get when you combine that proton with an electron? Well, you take a plus and a minus and you get a neutral charge, and it weighs 1 mass unit. So that's what a neutron is. A neutron is actually a particle that is made up of a proton and an electron.
So when that carbon-14, it's too heavy, it has too many neutrons hanging around, one neutron's going to kick off an electron and turn into a proton. Now it becomes nitrogen, which has 7 protons in the nucleus, and it still has 7 neutrons. So it's nitrogen with mass 14. So it's 14 nitrogen. So 14 carbon-14 turns to nitrogen-14. And
I'm really messing up here.
Chris's microphone's falling into his face. What's going on over there? You need to readjust? Having an earthquake over there in central Michigan?
So it feels like late fall here in Michigan right now, and it's cold. And so I have a hoodie on. Yeah, it's like 56 degrees right now. It shouldn't be this
just
cold.
A mess over there. You just interrupted my flow left and right, man. Come on.
Sorry. All right. I apologize.
All right, we'll summarize here. The point is that 14 carbon, too heavy. It breaks down, kicks out an electron, turns into nitrogen. Okay? That's radiocarbon. That's the radioactive version of carbon. Radiocarbon is radioactive carbon. Carbon-14 is the radioactive version of carbon. And this decays over time, and it has a half-life of 5,730 years. And half-life means that this thing's eventually going to decay away. So carbon-14 is going to break down exponentially over time. And Chris, you have an amazing analogy for this. Let's go through that analogy to understand half-life.
Okay. First, the half-life, like the textbook definition of it, is the time it takes for 1/2 of the atoms that are present to decay. So we've talked about this before in previous episodes. It's a shoebox analogy. If you take an empty shoebox and you put 100 pennies in it and you close the lid and you shake it up, however many shakes you give it, right? You shake it up a bunch and you open up the lid. I have to remove, let's say, all of the tails. If I put in 100, how many statistically should I remove?
Round about 50.
Yeah, right. I'm going to remove 50 of them. So that's one half-life. I remove 50. So now I have 50 that are head side up in my shoebox. I close the lid and I shake it up again. I open it up again. And now how many statistically should I remove?
Round about 25.
25. That's how half-life works. It is half of the half of the half. So if each time I do this, where I close the lid and I shake it up and then I open it up and I remove the tails, whatever time span you want to pick, does that represent 1 day? Does it represent 10 days? Does it represent, in the case of carbon-14, 5,730 years? That's the half-life, the time it takes for one half of those atoms to decay. So the first time I did it, I removed 50. And like rookie students want to say, well, okay, the next time you're going to remove the other 50. No, I don't have 100. It's half of the half. And that's the way atoms decay as well.
And this is the beauty of this analogy, Chris, is because that coin flip scenario, anytime a coin is flipped, it's 50-50 chance. It's a probabilistic thing. Like you might get 10 heads all in a row, right? You might have that one coin left for many, many half-lives because it's, randomly getting lucky and it's staying in there. But every flip, it's 50% chance. That's the same thing as radioactive decay. Every atom has a fixed probability of decaying in a year, and that probability just equates up to a half-life. We can scale that up, and it becomes a half-life when you have billions and billions of atoms sitting there. So it's a perfect analogy for radioactive decay, Chris. It really, really works well.
And there's a point to make here, I think, is that every radioactive element, and only certain atoms are radioactive, only certain isotopes are radioactive. They're radioactive because they have an unstable nucleus. There's nothing that changes that isotope's rate of decay. No temperature changes, no pressure changes. The half-life is what the half-life is. The time it takes doesn't change. And each isotope, though, has its own identity for half-life. We go to like long extremes, right?
Yeah, and so if you're sitting there listening, you should be raising red flags in your head right now about radiocarbon because your shoebox analogy, Chris, you're thinking, okay, we've got a bunch of carbon-14 atoms. Let's say we got 1 billion of them. And a half-life, 5,730 years. We open up the shoebox and we take out half. And then we do that again. And 5,730 years later, we do it again. And we do it again and again and again and again. And pretty soon, there's no more carbon-14 kicking around. Where's the carbon-14, right? We're going to run out. So why is this a useful system? Why is there carbon-14 around on Earth ever? And the answer is that it's different from other isotope systems that we have talked about on this podcast. We talked about in our ancient nuclear reactors, and in a couple different episodes, we've talked about uranium.
One of my favorite episodes, by the way.
It was a great one.
Go back and listen to Ancient Nukes. That was a great episode. I think. I'm proud of that one. That was fun.
I agree. That was a really fun one to do. But uranium-238, there's a uranium-238 isotope. There's a uranium-235 isotope. They're both decaying away. They're decaying at different rates. Uranium-235, we're almost 6 half-lives into the decay of uranium-235 from the start of the solar system. So there's not much 235 uranium around on Earth anymore.
We're only 1 half-life into uranium-238.
So there's a bunch of that around still. Carbon-14, if it has this really short half-life, why is it still around? And the answer is that it's constantly being produced. So carbon-14 breaks down to nitrogen-14. Actually, in the upper atmosphere, nitrogen-14 is interacting with cosmic rays and being turned into carbon-14. So carbon-14 is being actively produced in Earth's upper atmosphere. And this means that your shoebox analogy, Chris, I think we need to modify it just slightly. And so every time we're going to take this analogy, and every time you open up that shoebox, I'm going to dump some more coins in. So you're going to take out all the tails, and I'm just going to chuck some more coins in there. How do you feel about that?
Well, that conjures up a funny mental image of me doing my little shoebox analogy and very regimented, very focused. And then I got the little devil over there, Jesse, just dumping in random carbon-14s when I open it up. Like,
I've got this vision of you up in front of your class trying to, explain, radioactive decay to your students, and you're opening up your shoebox and I'm sneaking in behind you, chucking them in over your shoulder. And Chris is like, what the hell? Why are these things not decaying away? What's going on here? So
first of all, you're a piece of work. Okay. But second of all, I don't know where you're going with this, because two things. You're right. Carbon-14 is regenerated in a way that most radioactive isotopes are not. But I don't see why it matters. I don't see why you have to be dumping in carbon-14 into my shoebox. So explain that.
Sure.
Does that make sense?
Yeah, absolutely. So it's a great question. Leads right into, I think the key point is we need a way to stop me from dumping in new coins into the shoebox, right? And
isn't that just death?
Exactly. That's what it is. So if your shoebox is the atmosphere, then carbon is always being produced, carbon is always decaying, and carbon's turning into nitrogen, nitrogen's turning back into carbon, etc. We need a way to stop me from dumping in those extra coins. We need to, you need to lock me in your little back office of your classroom so I can't dump coins in there anymore. And then that is death. We are living right now. We are respirating. We're breathing in oxygen. We're eating carbohydrates. We're taking carbon out of the atmosphere eventually through our food and putting it into our bodies. When we die, that process stops and that carbon is no longer exchanging with the atmosphere. And now it's just you and your shoebox.
So the ratio of carbon-14 to carbon-12 in our bodies when we die is representative of the ratio of carbon-14 to carbon-12 in the air at the time we die.
Basically, yes, exactly.
Okay.
Yes, it's very close to the air ratio. So you are, if you died tomorrow, or if I died tomorrow, we would stop exchanging carbon with the atmosphere and with the food and with the water through our bodies. All that carbon-14 would be locked in our cellular structures and it would decay away to nitrogen-14. And so basically, we don't actually need to measure nitrogen at all in this system. So when we talked about uranium-lead dating, uranium-lead geochronology, we need to measure uranium, the parent, and lead, the daughter or the product isotope. For this system, we only need to know how much carbon-14 is there in the thing. Chris, if you have a lot of carbon-14 in your body and you're, laying there on the street, I can think, oh yeah, actually you died pretty recently. If there's no carbon-14 in you, you died a long time ago because all that radiocarbon decayed away.
And I know the limit probably isn't quite 10 half-lives. Is that right? It's not 10 half-lives, is it?
It's a little bit more than that for radiocarbon. People are pushing it up to 80 to 100,000 years. Wow. So we're like 20,000 times. Incredible. Yeah.
Because I want everybody to understand, when you go through 10 half-lives, you have 0.1% of the carbon-14 left. No matter what you started with, it's 0.1% left. After 10 half-lives, virtually nothing is left at that point. That's my point. Okay.
Very, very, very little. Yes.
Very little. And it's amazing to me that they're pushing that even like further. And that's a lot further too, by the way.
Yeah.
But that's awesome.
No, it is.
Wow.
It's crazy.
Okay. So basically what I can say is if we started with 100,000 atoms of carbon-14 in something, after 10 half-lives, we have 100 atoms left. So there's very little left, right?
Yeah. So Chris, I think at this stage, we should just step back, re-summarize the shoebox analogy with me adding coins in, make sure we're all on board with where we're at right now, because we're going to add another layer of complexity to it.
So basically, something that was alive dies. And it had 100,000 atoms of carbon-14. But it died 57,300 years ago. That means it went through 10 full half-lives. So at that point, I went from 100,000 parent isotopes, atoms, to 100. That's all that's
Yes.
left. Okay, that's 0.1% of 100,000. So there's virtually nothing left. That's pushing the limit of what we're able to test
Or, and you said that actually we can go further than that, which is absolutely amazing because there's so little left at that point. So that's just a summary of the shoebox analogy.
Beautiful, Chris. So the shoebox analogy then is that if you're in front of your class, you're teaching radioactive decay, you're shaking the shoebox, you've got your 100,000 coins in there, you shake it for one full shake, and that is equal to 5,730 years in radiocarbon half-lives. And then you open it up and you're going to take out half of them, you're going to take out 50,000. Radiocarbon, though, remember, in the upper atmosphere, nitrogen is turning into carbon. And so I'm sneaking up behind you, I'm chucking some coins into your shoebox here, and I'm messing up this number. Like I'm messing this up actively, right? As soon as you die, then I stop chucking coins in. You get sick of me and lock me in your little office, and then your shoebox just works perfectly, works beautifully. But the radiocarbon production rate is not constant. So the number of coins I'm throwing in at any given time, whenever you open up that shoebox, I don't throw in the same number. I'm not throwing in 20,000 every time. I'm throwing in 20,000 one time, 10,000 another time, maybe one time, and maybe 100,000 one time. Like I'm throwing in a different number of coins so that if you randomly die, if you just get fed up with me, lock me in your office, you might have not 100,000 coins in that shoebox anymore, but you might have 150,000 coins in that shoebox, which means that the time it takes to get down to 100 atoms is not going to be 10 half-lives. It might be 10.5 half-lives or 11 half-lives or maybe 9 half-lives. So it kind of disturbs our clock a little bit here.
Okay.
Does that make sense?
Hold on. No, it does not actually.
Okay.
It doesn't, to me, I'm just thinking this through. It doesn't mess up the clock. What it messes up is the limit to where you can take it. Look, the decay rate doesn't change. So that's where I'm a little bit confused about, like, all right, you're dumping in coins, but it really doesn't matter.
That is also true. I think let's put it in a real sort of a real world analogy. Let's say, Chris, you find a dead horse buried in some mud swamp somewhere, and I want to know, when did this horse die? I give you the thing, you make the measurement, you say, oh, the ratio of carbon-14 to carbon-12 is 1 to 10,000. For every one atom of carbon-14, there's 10,000 atoms of carbon-12. What does that mean for the age? How do we know what that means for the age? That gives us an age potentially, but how do we go about calculating that age? Because that's all the information we have when we're doing radiocarbon dating. Well, we have to know, what was the carbon-14 to carbon-12 ratio back through time? Because then we can calculate how many half-lives did this thing go. So we have to know, oh, actually back in time, there used to be 1,000 14 atoms to 12 in the atmosphere. And that's constant through time, or it's varying through time.
Okay. I'm tracking now. I get you. So that begs the question, can we do this?
Yes, that absolutely. So,
okay. Because this leads to the misconceptions that we alluded to at the beginning of the episode. Jesse, let's go into that.
Let me ask you this. You probably run into these a lot in your classroom. Do you run across misconceptions about radiocarbon? And if so, what are the greatest hits that you come across?
Radiocarbon dating is the standard for all dating. Like, that's the number one misconception that I come across.
Interesting.
Like,
okay, we'll come back to that.
Everything comes back to, well, carbon dating. Carbon dating is junk. Because,
interesting.
Yeah, there's so much out there about radiocarbon dating and what it can do. And then some people know what radiocarbon can't do. And then people say, well, oh, if radiocarbon dating can't do this, then radiocarbon dating is junk.
Right.
And so that's the most popular thing that I come across, is that, radiocarbon dating is all over the map. And it's not, actually. This is very solid. I think if you're talking about somebody that really has done a little poking around with it, the most common misconception centers around, you don't know how much daughter isotope is present. And maybe there was a lot of daughter isotope present at the time the decay process started, and you're assuming that none of it was there. You're assuming then that the age is much older than what it really is. I encounter that fairly often.
So that's a really interesting point, because I think that brings us really nicely into the later stages of radiocarbon here, is how do we calibrate this curve? We've talked about, I'm throwing coins into your box here, or nitrogen is being turned into carbon at different rates back in time. How do we calibrate that thing? Well, there's several ways to do this. First off, tree rings are a really great one. So tree rings, really old trees, we can count the years. So we can start at today and go back in time. We can link up different trees, so dead trees plus living trees. We can link up the tree rings to make a longer tree ring segment. If we say, there's 3 really bad years and 3 really good years and 4 really bad years, that makes a little barcode that we can match up. So we can go back actually really far with tree rings, and we can radiocarbon, quote unquote, date those interior tree rings, and we can calibrate our production curve, our carbon-14 production curve, to a tree ring, which is a great way to calibrate this. We can also do it with artifacts of known ages. So, really well-known ages that are 750 AD. We can radiocarbon date that, and it helps us calibrate this production curve. And that's actually how scientists first discovered that carbon-14 production rates changed back in time, was looking at artifacts with known ages, and they were slightly off. They were a few years off, and so the production of carbon-14 had to have shifted back in time. So we can do this really well.
That is one of the most interesting points about this whole discussion to me, is how carbon-14 has changed, like kind of organically as time goes on, right? Let me give an example. My dad, love you, Dad. He's an old bird.
He's an old bird. I love that. That is such a gentle way of that is great. I'm going to use that. That is awesome.
I do love you, Dad, but he was alive during the 50s and 60s. And
great point.
We were doing a lot of above ground testing of nuclear bombs. And that process created a lot more carbon-14. And then through photosynthesis and through what we eat, right? These people that were alive at that time have more carbon-14 in their brain stems than you and I do.
It's just so interesting, right? I mean, humans have changed the radiocarbon production curve, or the carbon-14 to carbon-12 ratio, a lot. And another way that we've done it is by burning fossil fuels. So Chris, how much carbon-14 is there in oil or any fossil fuel, really?
Are you quizzing me right now? You're a dirty bastard.
A little quiz.
Well, Jesse, this ain't my first rodeo.
You've been around the block.
Yeah, I've been around the block. There's none. There's no carbon-14. No, because this stuff was during the Carboniferous time period. This is old coal.
The production of hydrocarbons, oil, that stuff was all formed from rocks. The stuff died a long time ago, tens of millions of years ago, hundreds of millions of years ago, right? Like
longer than 57,000 years ago.
That's right. So when we burn those hydrocarbons, we put a lot of carbon into the air, and it has no carbon-14.
Which means it's enriched in carbon-12. Yep, that's right.
So we're basically diluting the carbon-14 in the atmosphere now. So humans have messed up the carbon-14 to carbon-12 ratio a lot more than it normally would do with this variations in the production of carbon-14 via nitrogen bombardment. So, 5,000 years from now, humans are going to have to do a little bit more careful calibration of radiocarbon dates. But I think it's a really interesting thing that this production curve, at least I find this interesting. Chris, you're probably going to tell me I'm being a little bit too professorial or nerdy or whatever right now.
That's what
too
I call
doctory.
you.
That's the
Doctory.
term. Too doctory. I'm being too doctory. But it gives these really production rate curve, the variations in radiocarbon production rate, so carbon-14 production rate, give us weird uncertainties. For instance, some of the Dead Sea Scrolls have been dated by radiocarbon. And because of this calibration curve, this variation in the production of carbon-14 back in time, it gives us two different age range possibilities. Like I'm used to thinking of uncertainties as, oh, that rock is 10 million years old, plus or minus 1 million years. So it could be 9 or it could be 11.
Yeah.
With radiocarbon, however, we get like age groupings. So for one of the Dead Sea Scrolls, there's a 15% chance that it dates from 355 to 295 BC. And then there's an 84% chance that it dates between 210 and 45 BC. So there's kind of like two clusters of probability. It could be between here and here, or it could be between here and here. But it couldn't be in between those things. So it's a really interesting sort of nuance of radiocarbon dating.
All right.
You're giving me that look again, Chris. Am I totally in the weeds?
Like, how does that? Okay. No, I don't think so. I think that's super interesting. How does that support the idea that radiocarbon dating is solid science?
Ooh, good question. Two things. It says that, hey, we're very aware of the uncertainties in this system. We're very aware of it. We're aware of this back in time, this variation in the carbon-14 production curve. We're aware of that. We know that it's a potential problem, and we need to incorporate that in our uncertainties. So when somebody says it's a 15% chance it's in this range and an 85% chance it's in this range, that means they're being careful. That means that we understand this system enough to accurately apply uncertainty to it and be honest about the uncertainties. So I think it shows that we're doing it really well, actually. If you can say, I know how good I am at this. It's like, I don't know. I love basketball. A good player isn't necessarily somebody who's always good at shooting threes. You can have a really good player who's terrible at shooting threes and just stays away from shooting threes. And they're a really good player. And it's this kind of toolbox thing. Like radiocarbon's really good for certain things. You also shouldn't use it to try and date a 10 million year old rock because you're going to get a wrong answer. It's just not going to be useful.
That is such a good point. I'm really glad you brought that up because that is, this is an important point regarding radiometric dating that depending on what you're dating, appropriate isotopes need to be used.
Yes.
Not any radioactive isotope will do. And that's a very popular misconception with this.
That's right. You cannot use radiocarbon to date most rocks, most rock types. It just doesn't work. Actually, really any rock type for the most part. Historical artifacts, ancient carbon deposits, that sort of stuff, but nothing more than 50 or maybe even 100,000 years old. So
yeah, even within artifacts, people think that you should be able to date bricks or mortar using radiocarbon dating. And that doesn't work because there's no there's no carbon that's inherent in those products.
Got to have something that died.
Yeah.
And you're dating the time of death.
That's right. That's right. That's right.
Well, I don't know, Chris. What do you think? Is this a sort of a wrap?
I hope it's a wrap. It was a fun discussion. These are the kinds of things that you and I sit on my front porch and we talk about this.
That's right. That's right. Sitting there having a couple beers, maybe a whiskey, talking about carbon dating. It's so good. I think it's just really cool. And radiocarbon dating, if you ever have the chance to go into a radiocarbon dating lab, they're totally cool. It's a huge room that stores these instruments. To do this type of analysis is really difficult, and it's got to be really good to do it. And they're just impressive stuff. This whole technique is really, really impressive.
I guess the summary then that I want to end this episode with is a statement by you about radiocarbon dating. How solid are we talking?
Oh, very solid when applied appropriately. Radiocarbon is super solid. We understand the system really well. Don't try and date a rock with it because you're just using the wrong tool. You're using a screwdriver for a nail. Like, what are you doing? You're being an idiot, So go use something more appropriate. Use uranium, lead, geochronology, potassium, argon, something like that. Radiocarbon is great, though. It is so cool, and it has been such a massively important development for the geoscience community, the archaeology community, the history community. It's one of these techniques that has its fingers in all sorts of scientific disciplines now.
Mm-hmm. And again, one of the coolest things for me about radiocarbon dating and the way it's done is it involves mass spectrometers. And the idea that a mass spec can pick up the difference in mass between carbon-12, carbon-13, and carbon-14. That blows my mind.
It's so cool.
Go back to our episode on geoscientific discovery. It was an interview where I talked to Jesse specifically about mass spectrometry and how it's done. It's amazing stuff.
Yeah, we do cover mass spectrometers. Don't get me going. We should end it before we get on the mass spectrometer train, because we'll be here all night.
Yep. But I think that's a wrap. I think that's good. It was a different episode for us, but a lot of fun. I loved it. It's been too long. So
totally. Glad to get back at it, Christopher. Hey, follow us on all the social medias. We're at Planet Geocast. Send us an email, planetgeocast@gmail.com. We have a listener question episode coming up pretty quick, so get your questions in and we'll throw them in there. Mm-hmm. The best thing you can do, well, not the best thing, the second best thing you can do is leave us a review and a rating on your podcast platform. That really helps the algorithm.
And the best thing you can do is share this with somebody that you think would love Planet Geo and who cares about our amazing planet.
There you go. Peace.
That's a wrap. Cheers.